Today we are discussing another important concept in solid state physics known as Brillouin zones. Second part of this class will be a discussion on different types of bonds exhibited by crystals. Let's consider a two-dimensional lattice like this one. Choose a lattice point P. Then connect this point to all nearby lattice points. Now let's draw perpendicular lines exactly at the midpoint of each of these connecting lines. Now the polyhedron enclosed by these perpendicular lines are called the Wigner-Seitz cells. This is a primitive cell and it is possible to fill up all space by translation of that cell. In 3 dimensions, the Wigner-Seitz cell is a polyhedron obtained by connecting a lattice point to all other lattice points and drawing the planes perpendicular to these connecting lines and passing through their midpoints. So these are the Wigner-Seitz cells of a BCC and FCFC lattice. I have posted a link in the discussion forum which will enable you to draw Wigner-Seitz cell for various types of lattice. You can try that to clearly understand this concept. So we have seen what a Wigner-Seitz cell is. This Wigner-Seitz primitive cell in the reciprocal lattice space is known as the first Brillouin zone. This is a concept first developed by Leon Brillouin in 1930 to explain the propagation of electron waves in a crystal lattice. The concept of Brillouin zone is particularly important in the consideration of the electronic structure of solids. First Brillouin zone is defined as the Wigner-Seitz primitive cell in the reciprocal lattice. This is the smallest volume entirely enclosed by planes that are the perpendicular bisectors of the reciprocal lattice vectors drawn from the origin. There are also second, third, etc. Brillouin zones at increasing distances from the origin, but these are used more rarely. As a result, the first Brillouin zone is often called simply the Brillouin zone. So let's see how to construct a Wigner-Seitz cell in two-dimensional reciprocal space or K space, which is in fact the first Brillouin zone. The first step is to use the real space lattice vectors and to find the reciprocal lattice vectors and construct the reciprocal lattice. This we have seen already in the previous class. Suppose this is the resulting reciprocal lattice in 2 dimensions. One of the points in the reciprocal lattice is then choose as the origin. When constructing Brillouin zones, they are always centered on this chosen reciprocal lattice point. It is important to keep in mind that there is nothing special about this point P, as each reciprocal lattice point is equivalent due to translation symmetry. So draw a line connecting this origin point to one of its nearest neighbors. This line is a reciprocal lattice vector as it connects 2 points in the reciprocal lattice. Let's draw similar vectors to all nearest neighbors. Then draw a perpendicular bisector to these vectors. These lines are called Bragg lines or Bragg planes in the case of 3-dimensional case. Now the area enclosed by these perpendicular bisectors is called the first Brillouin zone. It is equivalent to the Wigner-Seitz unit cell of the reciprocal lattice. So the first Brillouin zone encloses a region closer to the origin than to any other point in the reciprocal lattice. Now consider the next nearest neighbors and draw perpendicular bisectors to these vectors. The area enclosed by these Bragg lines, excluding the area of the first Brillouin zone, is called the second Brillouin zone. The third Brillouin zone, which is given as green shaded areas here, it is slightly difficult to understand it and it becomes increasingly difficult to construct the Brillouin zones as we move on to the higher orders. However, to understand most of the properties of the crystals, we need to know about the first Brillouin zone only. We can see that the Bragg lines for the third closest neighbors are these blue lines. So we might think that this entire rectangular area, excluding the areas of the first and second Brillouin zone, would be the third Brillouin zone, but it's actually not. You can also note that the first Brillouin zone contains one lattice point, the second Brillouin zone 2, and the third Brillouin zone 3, etc. In general, the nth Brillouin zone can be defined as the area or volume if you look in three-dimensional case in a reciprocal space that can be reached from the origin by crossing exactly n-1 Bragg lines or n-1 Bragg planes for three-dimensional case. All Brillouin zones have same area in 2 dimensions or same volume in 3 dimensions. In 3 dimensions, the first Brillouin zone is the volume enclosed by a cube formed by Bragg planes to nearest neighbors and centered around this point P. We had seen in the previous class that the reciprocal lattice to a simple cubic lattice is a simple cubic lattice itself with lattice constant 2 pi by a. Therefore, the first Brillouin zone for simple cubic lattice is the volume enclosed by a cube with sides from minus pi by a to plus pi by a. In a Brillouin zone, there are several points of symmetry which are called critical points. The center of the Brillouin zone is called the gamma point for all types of lattices. For a simple cubic lattice, apart from the gamma point, other symmetry points are M and X, which are centers of an edge and face respectively, and another point is R, which is a corner point. This is just to give you an idea of what all are the symmetry elements in FCC, BCC and hexagonal lattices. You don't need to by heart it, just to identify the various symmetry elements of these primitive Bravais lattices. The Brillouin zones are used to describe and analyze the electron energy in the energy band structure of the crystals. The electrons present in periodic crystals are commonly referred as Bloch electrons or Bloch waves. Brillouin zones are the allowed energy regions in momentum space for electrons present in periodic crystals. These allowed energy regions have certain boundaries in momentum space. At the boundaries of Brillouin zone, the group velocity of the Bloch waves tend to 0. Consequently, the standing waves are formed at the boundary. In contrast, within the Brillouin zone, Bloch waves behave as traveling wave. Such a change in the behavior of Bloch waves from traveling to standing wave formation results in the origin of energy gap at the boundaries. This is commonly called Bragg diffraction of Bloch electrons at the zone boundaries, and it depends on the crystal structure under investigation. The magnitude of band gap and shape of energy bands are ultimately determined by the nature of the periodic potentials involved. We will have a detailed discussion of these things in a later class. We have seen that crystals are made of atoms or molecules. Arrangement of these atoms in a crystal is determined by the nature of bonding between them. Such bonds that hold the adjacent atoms at particular positions are formed by the compromise between various attractive and repulsive forces. The physical, chemical and electrical properties of materials strongly depend the nature of bonding in them. Therefore, it is important for us to have a sound knowledge of different types of bonding. Crystalline solids exhibit three types of primary bonding. ionic, covalent and metallic bonds. It is also possible to have more than one type of bondings coexist in solids. Properties of the matter depends the way electrons which orbit around the nucleus arrange themselves to form bonds. Apart from this electronic configuration, the nature of bonding is determined by the energy of the system as well. As you know, all bound systems should have a minimum energy in their stable form. When some atoms combine to form a stable molecule, it is implied that it is a minimum energy state. When two atoms brought closer, they first experience some attractive potential shown by this green dotted line up to some point. After that, the effect of the repulsive potential becomes predominant over attractive potential. So the resultant energy of such a system is plotted as the total energy U of the system against the interatomic separation R, and it exhibits a minimum at the equilibrium separation Re between the atom. That is, at R equal to Re, the energy has the least value and the bound system is stable. This energy is called the cohesive or binding energy of the molecule. The cohesive energy of a molecule is the energy required for the formation of a molecule by bringing neutral atoms from infinity to the position of equilibrium separation. It can also be defined as the energy required to separate its constituent atoms to infinity. Mathematically, we can represent that the attractive energy is proportional to mth power of interatomic distance, and the repulsive energy is proportional to the nth power of interatomic distance, and the total energy is the resultant of these two forces, where A and B in these expressions are some constants. The crystals formed by the bonding of atoms belong to one of three categories classified by their bonding, that is ionic, covalent or metallic. Molecules can also bond together to form crystals. For example, a van der Waals bond occurs due to the attraction of charged polarized molecules and is considerably weaker than ionic or covalent bonds. Many other types of bonding, sometimes more than one mechanism, also exist in solids. Let's now try to understand the basic features of these bonds. We begin by considering ionic bonding, as this is the easiest type of bonding to understand. Ionic bonding occurs between atoms of different electron affinity. It arises due to transfer of one or more electrons from one atom to another. A typical example is the sodium chloride crystal. Electrons transfer from the sodium atom to adjacent chlorine atoms, since the valence electrons in sodium are loosely bound and chlorine has a large electron affinity. After the electron transfer from the sodium atom to the chlorine atom, the sodium atom becomes a positive ion and the chlorine atom becomes a negative ion. This reaction looks like this expression shown here. Na plus Cl gives sodium positive ions and chlorine negative ions. The positive sodium ion and negative chloride ion experiences an attractive Coulomb force because of the charged property. The potential energy associated with this force is governed by the Coulomb energy, which is minus 1 by 4 pi epsilon 0 E square by R0, where R0 is the distance between the ions. As the sodium and chloride ions move together, the force of attraction between the ions becomes stronger and the NaCl molecule is formed. However, if the ions come too close, the wave functions of the core electrons in the two ions begin to overlap, and due to something called the exclusion principle, this action promotes the core electrons and hence the entire molecule into a higher energy state, so which is not energetically very favorable. The equilibrium separation distance, or what we call as the bond length, between the ions occurs when the molecule is in its lowest energy state. For diatomic sodium chloride, this distance is 0.236 nanometer. In a crystal, the positively charged sodium ions and negatively charged chloride ions organize into an extended regular array of atoms to form sodium chloride crystal. In an ionic bond, an electron transfers from one atom to another. However, in covalent bonds, an electron is shared between two atoms. Crystals can also be formed by covalent bonding. For example, covalent bonds are responsible for holding carbon atoms together in diamond crystals. The electron configuration of carbon atom is 1s2, 2s2 and 2p2, and hence there are 4 valence electrons. This electron configuration is 4 electrons short of a full shell. So by sharing these 4 electrons with other carbon atoms in a covalent bond, the shells of all carbon atoms are filled. Here you can see that this single carbon atom represented by the dark blue sphere in the picture is covalently bonded to the 4 carbon atoms, 4 nearest carbon atoms represented by the light blue spheres. Covalently bonded crystals are reasonably hard, difficult to melt, and are insoluble in water. For example, diamond has an extremely high melting temperature of 4000 Kelvin and it is transparent to visible light. Two other important examples of covalently bonded crystals are well-known semiconductors, silicon and germanium. Now coming to the case of metal, a metal consists of atoms that have given up their outermost electrons to form an electron gas or electron cloud which moves throughout the given material. The electrical interaction between the positive ions at lattice sites and the negative electron gas holds the metal together. So metallic bonding is basically a collective interaction of the mobile electron gas with metal ions. This type of bonds occurs when the number of valence electron is only a small fraction of the coordination number. In such cases, neither an ionic nor a covalent bond can be established. Note that in metallic bonding, valence electrons behave as a gas, whereas in ionic and covalent bonding, electrons are tightly bound to their parent atoms. For this reason, metallic bond is somewhat weaker than the ionic and covalent bonds. I have posted a video link in the discussion forum which will give you a clear idea about metallic bonding, so please watch it. Ionic, covalent and metallic bonds are called the primary bonds in solids. There are some other bonds usually established between the molecules and those are called secondary bonds. Examples are van der Waals and hydrogen bond. A hydrogen bond is a special type of dipole-dipole attraction when a hydrogen atom is bonded to a strongly electronegative atom. Hydrogen bonding usually happens in molecules with centers of positive and negative charges that do not coincide. The tendency of an atom to attract electrons to itself during the formation of bonds with other atoms is known as the electronegativity of the atom. This is different from the electron affinity, which is the tendency of an atom to attract isolated electrons. In the molecules where hydrogen bond exists, the hydrogen is attached directly to a tightly electronegative atoms, causing the hydrogen to acquire a positive charge. So let's consider the example of water molecule. Since the electronegativity of oxygen atom is more than that of hydrogen atom, bonding electrons are pulled more strongly towards the oxygen atom during the formation of a bond. This results in net negative charge at the oxygen end and a net positive charge at the hydrogen end of the molecule, and hence it constitutes an electric dipole. When we have many water molecules, a bond is formed between water molecules due to the attraction between the positively charged hydrogen end of a molecule and the negatively charged oxygen end of another molecule. These bonds are usually very weak bonds. We know that in the case of inert gases, the outermost shells of constituent atoms are completely filled. Similarly, in molecules like methane, outer electrons are fully involved in the molecular bond itself. In such atoms or molecules, ionic or covalent or metallic bonding is ruled out. However, it is possible for these molecules to condense into solid state due to molecular forces collectively known as van der Waals forces. Even if a molecule is completely nonpolar in nature, at any point of time, one part of the molecule may contain more electrons than the other part. This means, at least momentarily, every molecule may behave as though it is polar. As a result, electrical attraction holds them together. So, like hydrogen bonds, van der Waals bonds also rely on dipoles. That is a difference in charge between two molecules. But unlike hydrogen bonds, the van der Waals dipoles usually is not permanent in nature, but it's transient. Now we have a section on band theory in this module, which I will continue after discussing the quantum mechanics.